welcome to this video lecture series on communication engineering. I am Ramji, working as an assistant professor in the Department of Electronics and Communication Engineering at GCE Tanjavur. So today we'll be discussing about the following digital modulation techniques: BPSK, binary phase shift keying; DPSK, differential phase shift keying; quadrature phase shift keying QPSK; QEAM, quadrature amplitude modulation. Let us start with what is digital modulation. Digital modulation is a technique in which the characteristics of the carrier signal is changed in accordance with the amplitude of the digital modulating signal. Here, the digital modulating signal is a unipolar format and the carrier signal is a very high frequency analog signal. The high frequency analog signal is like this. So there is a carrier signal and we have a digital modulating signal will be like this. So after modulation, if only amplitude of the carrier signal is changed, that is called ASK. If the amplitude of the carrier signal is changed, that is amplitude shift keying. If the frequency of the carrier signal is changed, that is frequency shift keying. If the phase of the carrier signal is changed, that is phase shift keying. And if amplitude and phase of the carrier signal is changed, that is quadrature amplitude modulation. So PSK is a digital modulation technique in which the phase of the carrier signal is changed in accordance with the amplitude of the digital modulating signal. So based on the number of possible changes in the output, that is modulated signal, we have different types of PSK. This binary phase shift keying is the simplest form of PSK. Binary phase shift keying, also called phase reversing keying. Sometimes called bypass modulation. So in this technique, after modulation, the modulated signal will be having two phase changes. One is 0 degree phase changes, another one is 180 degree phase changes. If logical 1 is applied to the BPSK modulator, we have 0 degree phase shifted signal. If logical 0 is applied to the BPSK modulator, we have 180 degree phase shifted modulated signal. So there is a block diagram of BPSK transmitter. We have a balanced modulator. This balanced modulator has two inputs. One is sine omega CT from carrier oscillator, and another one is from a level converted signal. Depending on the logic condition of this digital data, we have a two different signal, in phase signal or out of phase signal. So there is a schematic diagram of balanced modulator. This balanced modulator has two inputs. One is binary data and another one is sine omega CT. Here, to operate properly, we have to follow one condition, that is the modulating signal voltage Vm, that must be greater than carrier signal voltage Vc, because the modulating signal voltage, it controls the on-off states of this diodes D1, D2, D3, D4. If positive voltage is applied to the balanced modulator, positive voltage means plus volt we can get from the level converter. If logic 1 is given to the level converter, we get plus volt. If plus volt is given to the balanced modulator, D1 and D2 are forward bias and on, D3 and D4 are reverse bias and off. So here D1, D2 are forward biased. D1, D2 are forward biased, D3, D4 are reverse biased. So as a result, carrier is developed across T2, that is in phase with the carrier is at T1. So there is no phase difference. Here the input signal like this, and the output also here, there is no phase difference, we get the signal like this. But in the case of negative voltage is applied, negative voltage means negative voltage, that is minus volt. Minus volt can get, if we apply logic 0 to the level converter, we get minus volt. If minus volt is given to the balance modulator, in this case D1, D2 are reverse bias and of D3, D4 are forward biased. So this D3 and D4 are forward biased. So as a result, carrier is developed across T2, that is 180 degree phase difference with the carrier is at T1. So we will get the signal, phase shifted signal will be like this. In the input signal it will be like this. So we have the phase shifted signal when we apply the logical 0. So if logic 1 is applied, D1, D2 are forward bias, there is no phase difference. If logic 0 is applied, D3, D4 are forward bias, we have 180 degree phase shifted modulated signal. So there is a truth table and phasor diagram of BPSK signal. If logic 0 is applied, we have 180 degree phase difference. Logic 1 is applied, we have 0 degree phase difference. So there is a phasor diagram, it shows a phasor value of modulated signal. And there is a cancellation diagram, it is similar to a phasor diagram, sometimes called state space diagram. It is similar to phasor diagram except entire phase is not drawn, only the relative peaks of phases are shown. For logic 1 we have 0 degree, logic 0 we have 180 degree. So this width represents the distance, that is the relative peak. So this is a BPSK modulated signal. If logic 1 is applied, there is no phase difference. If logic 0 is applied, we have 180 degree phase difference. So actually the carrier signal will be like this. So this is a carrier signal. Okay, so this is a carrier signal after modulation. If logic 1 is applied, there is no phase difference between carrier and the modulated signal. But if logic 0 is applied, there is a phase difference. So this is a carrier signal and this is a modulated signal. And this is a block diagram of BPSK receiver. The received signal may be plus sin omega ct or minus sin omega ct. Here we are having carrier recovery circuit, detect and regenerate the carrier signal, that is plus sin omega ct. Here balance modulator acts as a multiplier. It multiply this plus sin omega ct and the received signal. This low pass filter, it blocks a high frequency more than omega c. We have a level converter to convert polar to unipolar to get logical values. So the received signal may be plus sin omega ct or minus sin omega ct. So the mathematically we can, the demodulation process will be like this. If a plus sin omega ct is received, we have plus sin omega ct and there is a carrier signal, a recovered carrier signal plus sin omega ct. This two signal is given to the balance modulator. It multiply these two signals, so we get sin squared omega ct. We can write 1 by 2 1 minus cos 2 omega ct. So this is given the low pass filter. It filter the high frequency component more than omega c. So this part will be filtered. So finally we get plus 1 by 2. So this is given to the level converter to convert from polar to unipolar. If the value is plus 1 by 2, we get logical 1. If the received signal is minus sin omega ct, this minus sin omega ct and the carrier signal is multiplied in the balance modulator. So we get minus 1 by 2 minus cos 2 omega ct. So this is filtered by low pass filter. Finally we get minus 1 by 2, give it to the level converter to get logical 0. So if plus sin omega ct is received, we get logical 1. minus sin omega ct received at the receiver, we can recover logical 0. So next one is a DPSK, differential phase shift keying. It is a digital modulation technique in which the phase of the carrier signal is changed in accordance with the amplitude of the digital modulating signal. Here the digital modulating signal is x naught of present and previous bits. Here DPSK, instead of directly applying the digital value to the balance modulator, here we applying the difference between the two successive signaling in this DPSK. So to get the difference between the two successive signaling, we take this circuit. Here we have the x naught. Here the incoming information bit is x naught with the 1 bit delayed value. For the first data bit, there is no reference value, so we have to assume the reference value either logical 1 or logical 0. Here we use x naught, so the x naught truth table. If you have two inputs, then both are same, we get logical 1. Both are different, we get logical 0. So the truth table of x naught will be like this. So here the incoming information bit is compared with the 1 bit delayed circuit. If both are same, we get logical 1 from this x naught. If both are different, we get logical 0. So this is given to the balance modulator to get a DPSK modulated signal. Here there is a reference values. We take reference as 0. There is incoming information logical 1. If both are different, we get logical 0 from x naught. If there is a 0, there is a negative voltage is given to the balance modulator to get 180 degree and plus sin omega ct, minus sin omega ct signal. If both are same, we get logical 1. There is a logical 1, we have 0 degree phase difference signal. So this is a block diagram of DPSK receiver. We have balance modulator and 1 bit delay circuit. So the received signal may be a plus sin omega ct or minus sin omega ct. Initially we take the first bit as a first incoming signal as a reference signal. This reference signal is given to the balance modulator. Another one signal from the next signal, DPSK signal. So this balance modulator acts as a multiplier. It multiplies these two signals. Suppose if the reference value is plus sin omega ct and the received signal also plus sin omega ct, this both are multiplied, so we get 1 by 2 minus 1 by 2 cos to omega ct. So this is given to the low pass filter. The output from balance modulator is given to low pass filter to block high frequency component. Then we have the level converter from polar to unipolar to get logical values 1 or 0. Here there is a timing sequence of DPSK. Here there is a reference phase 180 degree and the incoming signal is 180 degree out of phase, means it is given to the balance modulator. If this is 180 degree means minus in omega ct, 180 degree minus in omega ct, both are given to the balance modulator, so we get plus 1 by 2. It is given the level converter to get logical 1. Then next case there is a reference value and there is an incoming received signal. It is given to the balance modulator. This is 180 degree means there is a minus in omega ct, 0 degree plus in omega ct, so we get minus 1 by 2 plus 1 by 2 cos to omega ct, give the low pass filter to block high frequency component to get minus 1 by 2 from a level converter. Then this minus 1 by 2 is given to the level converter to get logical 0. Next one is quadrature phase shift keying. Quadrature phase shift keying QPSK is an angle modulated constant amplitude digital modulation technique with 4 possible output changes. QPSK is having 4 possible phase changes. To get 4 possible phase changes, we have to apply 4 different input combinations. So the input combinations may be 0, 0, or 0, 1, 1, 0, or 1, 1. So the 4 possible changes, m equal to 4. So to get 4 possible changes, we have to apply 4 different input combinations. So it must be 0, 0, 0, 1, 1, 0, 1, 1. So there will be formula 2 power n equal to m. M is a number of possible outputs and n is a number of inputs. Here m equal to 4. So the n must be 2. So the 4 different combinations 0, 0, 0, 1, 1, 0, 1, 1. So this is a block diagram of QPSK transmitter. Here the input bits is given to the bit splitter, one bit is given to the I channel and the other is given to the Q channel. I bit modulates a carrier that is in phase and the Q bit modulates a carrier that is out of phase, that is in quadrature, hence the name is quadrature channel. Then the output from the top balanced modulator will be plus sin omega ct or minus sin omega ct based on the logical value. Similarly, the output from the bottom balanced modulator will be cos omega ct or minus cos omega ct based on the logical values. Then finally this two signals is combined, two signals are combined by linear summer to get the QPSK signal. Let us see what will be the mathematical equations when we give Q equal to 0 and I equal to 0. So when I equal to 0, I is given to the value is given to the balanced modulator. If I value is 0 means that is the negative voltage, that is minus 1. This from the carrier sin omega ct, so we get minus sin omega ct. Similarly in the Q channel, if Q equal to 0, that is a negative, that is minus 1. Then there is a out of phase carrier, that is cos omega ct. Then we have minus cos omega ct. These two signals are combined, we get minus cos omega ct minus sin omega ct. So mathematically we can read it in terms of magnitude and phase, that is 1.414 sin omega ct minus 135. That means if I equal to 0, Q equal to 0, we will get a signal with a phase shift of minus 135 degree. There is a truth table of QPSK. When I equal to 0, Q equal to 0, we have minus 135 degree phase change. I equal to 1, Q equal to 0, minus 45 degree. I equal to 0, Q equal to 1, plus 135 degree. I equal to 1, Q equal to 1, plus 45 degree phase change. There is a phasor diagram. It shows a phasor representation of these 4 possible changes 0, 0, 0, 1, 1, 0, 1, 1. And there is a constellation diagram. It shows a relative peak position of each phasor. There is a QPSK modulated signal. When I equal to 0, Q equal to 1, we have plus 135 degree change in the carrier signal. I equal to 1, Q equal to 0, we have minus 40 degree phase change in the carrier signal. I equal to 1, Q equal to 0, plus 40 degree phase change in the carrier signal. I equal to 0, Q equal to 0, minus 130 degree phase change in the carrier signal. So there is a block diagram of QPSK receiver. The received signal is given to the power splitter, that is given to the I channel and Q channel. I channel signal is given to the product director. The other signal from carrier recovery circuit, that is a plus sin omega ct. This product director, it multiply this I channel signal and sin omega ct. It is given the low pass filter. it filter the high frequency more than omega c, and finally we have a level converter to get the logical value of I. Similarly, the power filter signals go to the Q channel, one signal from Q channel, the other from 90-degree phase shift of carrier recovery receiver to this cos omega ct. It is given to the product detector. It multiplies these two signals. Then it is given the low pass filter to block the frequency more than omega c. Then we have the level converter to get logical value of Q. So let us see what will be the logical value when we receive the signal minus sin omega ct plus cos omega ct. This signal is given to the power splitter. Then we have the I channel value minus sin omega ct plus cos omega ct. Similarly, Q channel also we have minus sin omega ct plus cos omega ct. This signal is going to the balance modulator. One more signal from the carrier recovery circuit sin omega ct multiply. Then it is going to the low pass filter. It will block the high frequency more than omega c. Then it is going to the level converter to get polar value to unipolar. It is a logical value. If we have plus 1 by 2, we have logical 0. Similarly, the same signal is given to the Q channel. Then we have one more signal from the carrier recovery circuit plus 90-degree phase shift. And then these two signals are multiplied in the balance modulator. Then it is filtered by using low pass filter. We get 1 by 2 volt. It is given to the level converter to get logical 1. Next one is QAM, quadrature amplitude modulation. Quadrature amplitude modulation is a modulation technique in which both amplitude and phase are changed in accordance with the digital modulating signal. So based on the number of possible outputs, a QAM may be 8 QAM, 16 QAM, 32 QAM, 64 QAM like this. So we will discuss about how 8 QAM modulator is working. In this 8 QAM, we have 8 possible outputs. To get 8 possible outputs, we have to apply 8 different possible inputs. So here m equal to 8 possible outputs. The formula is 2 power n equal to m. M equal to 8, so 2 power n, so the n equal to 3. So n is a symbol size, so the symbol size must be 3. So the possible symbols are 0, 0, 0, 0, 0, 1 to 1, 1, 1. So to get 8 possible outputs, we have to apply 8 different input conditions like 0, 0, 0, 0, 1, 0, 1, 0 like this. So this is a block diagram of 8 QAM. So the input bit is given to the bit splitter, one bit is given to the I channel, one bit is given to the Q channel, and the other one is given to the C channel. So here we are using 2 to 4 level converter. It has 2 inputs, I channel and the C channel. By using this I and C, we get a PAF from 2 to 4 level converter. If I equal to 0 and C equal to 0 means we get minus 0.541 volt from PA, from 2 to 4 level converter. And this signal is given to the product modulator. If it is negative, we get a signal, negative signal. And similarly, the Q channel and the C channel is given to the 2 to 4 level converter. The output from the 2 to 4 level converter based on the value of Q and C. So if Q equal to 0, C equal to 0, we get 0.541 volt. This is given to the product modulator. In the output of the product modulator, top and bottom are summed by using linear sum to get 8 QAM signal. So if we have 8 possible phase changes in the 8 QAM, If Q equal to 0, I equal to 0, C equal to 0, we can get the QAM signal minus 0.541 sin omega ct minus 0.541 cos omega ct. Mathematically, we can rewrite this equation in terms of magnitude and phase, that is 0.765, and the phase value is minus 135. Similarly, we get the 8 possible changes. This is a truth table of 8 QAM. We have the symbols QIC. For this QIC, we get the 8 QAM output. This is a phasor diagram and the cancellation diagram. In this phasor diagram, it shows a phasor of 8 possible changes, and this is a cancellation diagram. It shows a relative portion of the peak of each and every possible outputs. And this is a graphical representation of 8 QAM signal. For 0, 0, 0, we have minus 135 degree change with the amplitude is 0.765 volt, and 0, 0, 1, we have minus 135 degree angle change with the plus 1.848 volt. Similarly, for all the input combinations, we have different phase changes and the amplitude changes. Next lecture we will be discussing about what is ISI, indecibel interference. Thank you.